The collision and moving of objects appears in nearly every interaction in our daily lives, so of course the same thing applies to our computer software as well. Video games, movies, both real-time and pre-rendered physics engines are used everywhere with a wide range of applications. Unlike in real life where these interactions just happen, within a computer program the positions, forces and velocity of each object have to be stored as a number. Those numbers are then manipulated when the simulations move forward a small amount of time, a large number of times each second. Those numbers are then used to display visuals on the screen, and when the visuals are updated each step of the simulation, it creates this illusion of movement, like a frame-by-frame animation of a ball moving across the screen. First, describing the position of objects. How would you describe the position of the red ball on the screen? There's no possible way I could hear you, but I'll guess you said something to the effect of to the right of the blue ball. As we're aiming to store the exact positions of objects for the purpose of simulation, we need to store the position in terms of numbers. In this example, the red ball is 5 centimeters to the right of the blue one. We can ignore the measurement unit from this point as it doesn't matter much as long as everything is stored on the same scale. But here's a problem. What if we move the blue ball 2 centimeters to the left? The red ball has not changed position, but the value stored to represent its position has changed. Anything that can be moved within the physics engine, i.e. any object that is being simulated such as the two balls in the scene, cannot be used as a point of reference for other objects' positions due to those objects being able to move themselves. This is a problem. But what if there was an object that didn't move? We could use that object as a point of reference for all the actual objects we want to move in the scene, instead solving the problem. Refer to this object's position instead as a single point called the point of origin. And with this distance to the right being represented with positive numbers, and distance to the left being represented with negative numbers, just like a number line, we can represent the position of the objects across this line. This line can be referred to as an axis. We can now represent the position of any object on a straight line using a single real number, but what if we want to move the red ball up here? Add another axis of course, just copy, rotate and paste, and by storing the second real number for each object, we can now store the position of any object in this two-dimensional space. The two values describing the position of an object in 2D space in reference to a fixed point can be referred to as a vector. We could also add a third axis going into the screen so we would be able to represent a three-dimensional space, just like in real life. But let's just say that would make things much more complicated, so we'll just stick to the 2 dimensions to keep things simple. Now we can express the position of objects, let's get started moving them. As stated earlier, most physics engines work by stepping for the simulation a small amount of time, a large number of times each second, and displaying the results from each step onto the screen in quick succession, creating the illusion of movement to the viewer. In this example, we refer to the time that's passed since the last step has occurred with the name delta. By adding 5 times the delta value to the first value of the position vector of the ball, this will result in moving the ball 5 units to the right each second. But that's not exactly how the ball would move in real life. It would move downwards because of the gravitational force of the earth acting on it, unless you were in space of course, but let's just ignore that. Just move the ball down 5 units each second instead by taking away 5 times delta from the second value of the position vector But that doesn't exactly look right, does it? When an object falls down to the gravitational forces, it's not at a constant speed. The speed actually increases as time passes. The best way to model this motion is Newtonian physics, which does a pretty good job replicating the properties of our physical world. That might sound complicated, but what it basically means in this stage is that we'll apply 2 rules. 1. Objects must remain at the same velocity unless a force is applied on it, and 2. The acceleration, increase in velocity, is equal to the force applied divided by the mass of the object. Now, by storing the current velocity and mass of the objects, with the mass being stored as a single number and the velocity being stored as a vector with 2 values corresponding to the current velocity in each axis, we can now create a more accurate simulation. Now, on each step for each object, we can set the downwards force for the object to that object's mass multiplied by the gravitational force constant, calculate the corresponding acceleration, add the acceleration multiplied by delta to the velocity of the object, and finally add the velocity times delta to the position vector of that object. Finally, accurately simulating a ball falling down, and we forgot about collisions, didn't we? While the ball is accelerated downwards at an appropriate rate when ignoring things like air resistance, the ball just faces straight through the floor. For the ball to actually land on the platform, we need two things. Number one, a collision detection system, which checks if there is a collision and stores data about it so it can be acted on by. Number two, a collision response system, which determines and carries out an appropriate response to each collision for each object in the simulated space. For our system to work, we not only need to find a list of all pairs of objects which are overlapping, we also need to find the point within object A that is furthest into object B, and the point within object B which is furthest into object A, allowing us to find all the data required for the collision response system to create an appropriate response. But before we do that, we actually have to define the space that each object takes up in terms of numbers. Up until this point, we've only actually defined the exact and infinitely small position of the object. To define the shape and size of an object, we assign an object known as a collider to every simulated object within the physics engine. A collider also contains the code required to calculate the data points required for the collision response between itself and other types of objects. Colliders can represent rectangles, hexagons, and even irregular shapes, but for this video, let's just stick to a single type of shape: circles. You might not realise it, but circles are the easiest shape to do collision detection for. That's because the entire shape can be defined as a single number, its radius, or its diameter if you want to go there. And its actual physical shape, get the object position, draw a line through it with the length of 2 times the radius, do that a million times, and you got yourself the shape of the collider. Want to know if two circles are overlapping? Just find the distance between the two object positions and check if it's smaller than or equal to the two objects' radiuses added together. This can be found by first finding the vector between the two positions by taking away one object's position vector from the other, by drawing both of the vector's components head to tail, and then the line between the beginning and the end of the journey. What do you get? A right angle triangle, of course. So by using the Pythagorean theorem, a squared plus b squared equals c squared, we can conclude the square root of x squared plus y squared will result in the distance between the objects, or the magnitude of the vector between the two position vectors of the objects. Using this logic, we can then go on to calculate the furthest point of intersection of both objects. We can also find the direction of the collision, which is the vector between the two objects' positions divided by its magnitude, resulting in it being in the form of a unit vector with a magnitude of 1. Using circles just makes all of this so much more simpler. These operations have to be completed for every possible pair of objects within the simulation for every step forward in time the simulation takes, allowing us to find a list of all the pairs of objects colliding at a single point in time with all the data about said collisions. And with this, we can create a collision response for every collision that has taken place within that step. Our collision response will aim to be as simple as possible and contain only 2 steps. 1. Change the position of each object in a collision to make sure that the objects don't appear as if they're overlapping each other, and 2. Modelling an impulse, adding a force with an appropriate magnitude and direction to both objects to drive them apart after the collision has taken place. This gets us closer to our goal of making the objects behave in a way we would expect them to, acting in a similar manner to how 2 balls would collide in the real world. First, we need to make sure the objects' colliders aren't actively colliding by the next step iteration, in this example meaning that the 2 circle colliders aren't overlapping in any way. We first get the vector between the 2 objects' positions. This is found by multiplying the direction of the collision vector by the distance between the 2 objects we found earlier. We then take that vector from the position vector of the first object and add the same vector to the position vector of the second object. Now the circles aren't overlapping. Next is to deal with the effect of impulse, with impulse being the change in momentum, mass times velocity. For this we need 3 values: the masses of both objects we have stored within each object, along with the component vector of the differences between the velocity vectors of both objects, but only the component which is aligned along the axis of collision, the vector which represents the differences in the positions of both objects, which we have found earlier. This is difficult. If we were just decomposing the vector along the coordinate axes, we would just take each number that makes up the vector as its own component, but when the components we're looking for aren't aligned to the 2 axes, it then becomes much more difficult to determine how we're supposed to split it. To make things simpler, let's refer to the vector of the difference between the 2 objects' velocities as A, and the vector representing the axes of collision as B. So our goal is now to project vector A onto vector B and store the result. We can use something called a dot product to find the projected vector's magnitude. The dot product is an operation that can be carried out between two vectors, multiplying each component of the first vector with the second vector's equivalent components and adding all those values together, resulting in a single number. In simple terms, its value represents how similar the two vectors are to each other. When one of the vectors is a unit vector, it will give you the exact length of the non-unit vector, which is in the direction of the unit vector. For example, each component of a vector can be written as the dot product between the full vector and the unit vector in the direction of the respective axis. The dot product between the vector and the unit vector representing the x-axis will result in the level of the vector which aligns with the x-axis, as the y value is multiplied by 0 and left out completely. The same also applies to the y-axis. The dot product between the same vector and a unit vector aligned with the y-axis results in the length of the vector which aligns with the y-axis. This logic can be applied to project any vector onto any axis represented by a unit vector, meaning the dot product between vector A and the unit vector of B will result in the magnitude of the projected vector, the value that we are looking for. After storing that value, we first check if it's negative to make sure our impulse won't join the objects together, only continuing if this condition is fulfilled. We then divide it by the total mass of both objects. This value is then multiplied by the first object's mass, negated, and taken away from the first object's velocity. The dot product divided by the total mass of both objects is then also multiplied by the second object's mass, and then added to that object's velocity as well. A change in position is then carried out for each object depending on its current velocity and time since the last step has taken place. And after applying all these processes with every step moving forward the simulation in real time, we get something like this. This might seem simple, but the mathematics and algorithms featured in this video are the building blocks of much more complex physics engines with much larger scopes. And now you, yes you, understand those building blocks. So when you look upon a game or piece of software which contains something as simple as a ball falling and landing on a platform, now you can say, wow.